Hi, my name is Dr. Chen, and this is a video tutorial on how to conduct a multi-group confirmatory factor analysis. This is based on Chapter 7 on Timothy Brown's 2015 CFA for Applied Research textbook, which is a textbook that I use to teach a class on psychometrics. Couple of things before we get started. Special thanks for Dr. Buchanan for letting me borrow her one of her data sets and using one of her tutorials for this particular tutorial. There are some minor changes that I made here and there along the way in the analysis, but again, thank you so much for Dr. Buchanan and the stuff that she does in her stats lab. Now, for this particular tutorial, it is going to be based on a 14-item resilience scale, as seen here on the screen. This is a measure that supposedly gets at one's resilience. And so we've got 14 items over here. There are a couple of correlated errors between some items, as will be specified in this tutorial. But for the most part, this is supposed to be a unifactorial structure. And we are going to conduct a multi-group confirmatory factor analysis across genders to see how well this measure holds up whenever we start to impose constraints across factor loadings, across intercepts. And if there are some degrees of a lack of invariance across these different levels of invariance, we'll take all those into account and we will estimate a latent mean score across the two different groups that we'll be comparing. And specifically, we'll be comparing males versus females. All right, so this is the program that we'll be using to conduct a multi-group confirmatory factor analysis. First of all, what we will need to do is we will need to set the working directory. And so obviously this differs from computer to computer, but this is basically the path directory for accessing. Hi, this is Dr. Chen, and I am creating a video tutorial on how to conduct a multi-group confirmatory factor analysis. This is based on Timothy Brown's 2015 book called Confirmatory Factor Analysis for Applied Research. It's a really good book that teaches you all the nuances that go into conducting a factor analysis, specifically anything that is within the SEM or confirmatory framework. Now, one of the first things that I do want to show you is the instrument that we'll be working with. And the instrument that we'll be working with is the 14-item resilience scale. And this is a measure that is supposed to get at one's resilience. In the literature, this has historically been a unifactorial structure, the meaning only one factor. There are some correlated errors in this particular demonstration here, which I'll specify what those things are. And within the context of a multi-group CFA, we'll be comparing the factor structure of this instrument across males and females to see if they are invariant in terms of configural invariance, in terms of metric invariance, in terms of scalar invariance. And if you do find some degrees of a lack of invariance, we will we'll basically take those into consideration before we estimate an estimated factor means across those two groups. So we get a more accurate and fair measure of the estimated latent score for males versus females. So in the interest of time, I've actually written up the syntax for conducting this syntax. And by the way, special thanks for Dr. Buchanan, who is at Missouri State University, for letting me borrow her data set, as well as to use her tutorial as a base for me to create these tutorial. There are some minor differences here in the way in which I go about this analysis. But nonetheless, special thanks for Dr. Buchanan for letting me use her stuff. Now, first of all, we need to set the working directory, and this is going to differ from machine to machine. This is basically the path directory as to where the data set is located. Now, it's important that you also save your syntax, your R Markdown document within the same folder of your data set as well. And when I run that, actually, let me clear my workspace here. So we're starting with a clean slate. When I run that, you can see over the bottom here at the console that we set the working directory, and we're going to use the read.csv function to read in the data. In this data set, there are 516 observations with 17 variables. Now, what are those things? Well, let me show you the data set in Excel. Here we go. So the first three columns are basically demographic columns ranging from sex, race, and ethnicity. And then the item itself actually starts from the fourth column, RS1, all the way to RS14. And there are 500 and what was it? 516 observations. It says 517, but that's because the first row is they're basically the hitters. So 516 observations with 17 variables, 14 items, as well as 3 demographic variables. If I use a summary function, this gives me basically a summary of each variable right here. And this includes the minimum, maximum values, the median and mean for each variable, as well as the first and third quartiles. Now, first of all, let's identify some multivariate outliers. And to do this, we're going to use the Mahalanobis function. And we are going to exclude the first 3 columns in our data set. And we're going to extract the column means from our data set. And NA.RM equals true. That basically means to use only those cells that have data in them, because as can be seen here, there may be some missing data. Actually, hold on. There may actually not be, there may be no missing data. So this is actually redundant right here. So I'm gonna go ahead and remove this line of code here. Same thing to use equals pairwise.complete.ops. I'm gonna remove that as well. All right. So what this does is that it creates, think of this as we are creating a column, and that column is basically going to give the Mahalanobis values for each person based on their based on the means and the variance covariance matrix. If you want to get a summary, basically we will just use the summary function, and as you can see, the minimum value of that's locking screen. The minimum value of the Mahalanobis values in this data set is 0.7241 with a maximum value of 67.7582. In order to figure out the cutoff score that is associated with p less than 0.001, with basically 14 degrees of freedom, which is the number of columns in the data set except for the first 3 columns, the cutoff score is 36.12. So any person that has a Mahalanobis value larger than 36.12 is considered a multivariate outlier. And based on this result right here, we can clearly see that 28 people do not meet the criteria in terms of their Mahalanobis values. So we're going to remove those multivariate outliers using this subsetting function right here. So we only want people whose Mahalanobis values are less than the cutoff. Right. Next, now that we have removed all those multivariate outliers, we are going to check to see how we're doing in terms of our multivariate normality assumption. To do that, we'll need MV norm test as a package. We will need to transpose the data set such that the rows are the variables and the columns are people. And if we use the view function, this gives us a sense of how we actually transpose the data set. Using the QQ norm function, we can see here that there may be some violations here, I think, in terms of normality, because what we typically want is we want the diagonal line whenever we plot the theoretical quantiles coming from a multivariate normal distribution and the quantiles coming from a sample data set. So let's make a multivariate normal histogram using the R companion package. And the function here is plot normal histogram with N and H capitalized. No out is the data set. Whenever there's a space here, if we're subsetting the data set, the first space basically means that we are including all rows, that means all people, but we are excluding the first three columns, and that comes after the comma here. Probability is false because this basically changes what is on the y-axis, is either frequencies or probabilities. Either way, we're going to get about the same shape here. As can be seen here, this is not really normal. So I think there are some violations here in terms of multivariate normality. What that means is when we run our analysis, we want to try to use weighted least squares or some type of estimator that is robust towards violations of multivariate normality. Now, given that we're going to do a multi-group CFA, let's set up the data to have factor variables. And so we're going to use no out, and when we put the dollar sign followed by the name of the variable, that basically helps us to extract data from that particular variable. And we can see over here that 233 people are categorized under group 1 and 245 are categorized under group 2. Now, given that, when you do a multi-group CFA, it's usually a pairwise comparison. And so given that we only have one person who is in a third group, we're going to remove that one person, saying that, we're going to remove that third column, basically, using this subset function. Now, we are going to tell R that basically that we want to name what these columns mean. And so factor is the name of the function, followed by no out, which is the name of the data set. And specifically, we are referring to the sex variable. We're going to add the labels column equals to women and men. When we make that, when you check to see what has happened, we can see that, in the first column, which is group 1, they are known as women. And in the second column, they are known as men. Then we're going to make two data sets, because when you do a multi-group confirmatory factor analysis, we need to run the CFA separately in groups before combining them into one single matrix. So no out, where we would only want whose sex are identified as men, and the other one for women. Now, there's a couple of packages that we will need to run the multi-group CFA. We'll need Lavon, we'll need Semplot to make the measurement diagrams. To do the measurement invariance analysis, we'll need SemTools. And towards the end of this tutorial, we will calculate the effect size when we compare the estimated latent means. And so we'll need effect size or EFF size as the package to be able to do that. All right. So let's start out by creating a general CFA model that we think would apply to both men and women. In this particular write-up right here, equals tilde basically means that what comes before is the latent factor, and what comes after are the indicators. Now, whenever we see tilde tilde, this means that there is a correlated error between two items. And in this particular instance, for this particular sample, there is reason to believe that RS6 and 7 have correlated errors. So for example, if you look at RS6 and 7, you get that I'm determined, I can get through difficult times, which maybe that might cover a facet of resilience that might be a little bit different compared to, say, something else like discipline or keeping interest in things. Same thing also with RS1 and 3. That covers I usually manage one way or another. I usually take things in stride. Again, that may be referring to how flexible one might be. And again, when I did an exploratory factor analysis on this measure to see if there are several factors, there's only one very clear factor that came out. And so it could be that these items that have correlated errors have enough of a unique variance over and above the shared variance that they have with all of the other items, but common enough with each other that we would add that correlated error. And I did the same for RS8 and RS9 for similar reasons as well. All right. Now, when you build this model, make sure that you start out with the single quotation mark and you end with the single quotation mark. And we're going to call this overall model. So first thing, let's calculate the overall fit indices for men. So the function is CFA, and this is going to be based on the overall model that we just created. We're going to run this analysis on on the men data set, which is right here, excluding columns 1, 2, and 3, because those are the demographic variables. And we want the mean structure. Basically, we want to estimate the intercepts for the indicators and the factors. We're going to call this men.fit. So let's get a sense of the parameter estimates using the summary function. We're going to pull the parameter estimates from men.fit. Standardized equals true. That means we want the fully standardized values in the output. R square basically means that we want the R squares for the unstandardized factor loadings. Fit.measure equals true. That basically means that we want the global fit indices as well. Now, when we look at the parameter estimates, it's really important that we, first of all, check for Haywood cases. Haywood cases typically show up due to a number of reasons. It could be that your model is misspecified. It could be that there are data entry errors. It could be that your model is too complex. Most of the time, it's usually because the model is misspecified. And what happens is that because your model is doing such a bad job of reproducing the variance covariance matrix, it is forced to create parameter estimates that are out of bounds, that basically don't make sense, just solely because it is trying its best to recreate the elements in your sample variance covariance matrix. Typically, Haywood cases show up as negative error variances, so I typically look at this to see if there are any negative values in terms of the error variances. R squares, if you see any R squares that are more than 1, that is out of bounds, because this basically represents the amount of variance in an indicator that is explained by the latent factor, so it cannot be more than 1. If we look at the standardized factor loadings under std.all, none of this should be more than 1 in this column right here. And so I think we're good in terms of Haywood cases. Let's look at the overall fit indices. Now, in terms of chi-square, it is a statistically significant chi-square. So that means that there is a significant difference between our sample variance covariance matrix and our model implied variance covariance matrix. Something to note here about the chi-square global fit index is that it tends to be very sensitive towards large samples. So this tends to always be significant regardless of what the actual results are. So we'll also look at other global fit indices. Specifically, we'll look at the comparative fit index and Tucker-Lewis index. And for these values, we want them to be more than 0.90. 0.95 and above is really good, but 0.90 and above is adequate. And so it looks like we're doing good in terms of that. In terms of REMC, which is another type of absolute fit index that takes into account model complexity, we want this value to be less than 0.08. Ideally, we would want the 90% confidence interval to be less than 0.1 as well, and this to be less than 0.1. Basically, REMC that is less than 0.1 is adequate, less than 0.08 is good. So I think we're good in terms of our REMC. You can also look at the standardized root mean square residual, which is another index of absolute fit, and we want this to be 0.08 and below. So what I did was I created an Excel spreadsheet to help me keep track of these global fit indices. And I want us to focus here at the very top in row number 3, because right now all we're doing is we are imposing this CFA model on the data set consisting only of men. And I've transferred those values onto these cells right here. So the ones that are in green indicate good or adequate model fit. The ones that are in yellow suggest that maybe not so much. So across the board, all the global fit indices suggest that we're doing a pretty okay job in terms of reproducing the variance convergence matrix, probably because we got a fairly large sample. This p-value is going to be statistically significant. So overall, we are doing good in terms of goodness of fit indices. Now, if you wanted to get the confidence intervals for parameters, you can use the function parameter estimates, put in the model that you just ran, and ask for standardized. Basically, what this does is that it gives you the confidence intervals for the unstandardized parameter estimates. For instance, the factor loading for RS2 on the latent factor resilience, the unstandardized factor loading is 1.351. Basically, what that means is that as the latent factor goes up by 1 unstandardized unit, your indicator goes up. Basically, your questionnaire, which is on a scale of 1 through 7, goes up by 1.351 units. And the confidence interval for this is 1.030 and 1.671. Basically, we can be 90% certain that this the true value of the parameter estimate for RS2 on the latent factor is between these two values right here. Usually you need this for, say, if you're reporting this in a peer-reviewed paper. Now we can also look at modification indices. And so the function here is modification indices. And sort equals true. That basically means that we want the suggested model specifications to be sorted according to how large the modification index values are. And we only want those model respecifications whenever their MI value is larger than 3.06. Now, when you look at this, you got to be really careful because the software is almost always going to come up with a bunch of suggestions that may or may not be representative of the true specifications that you should be doing. For example, if you look at RS3 and RS4, it is suggesting adding another correlated error between these two items. If you're to do that, your estimated decrease in terms of the chi-square global fit index goes down by about 30 points, which is great. And the estimated correlation between these two error terms between RS3 and RS4 is 0.3, which is about a medium-sized correlation. But we need to also make sure that any model respecifications make theoretical sense. If you look at items 3 and items 4, I don't really see any reason why items 3 and 4 should be together. So it could be that this model respecification is being driven by some type of unaccounted source of error. And so I'm not going to do that. And typically, I only look for model respecifications that have at least a medium effect size, which is 0.3 and above, if not a large effect size, which is 0.5 and above when it comes to correlations. And this is the only one that has an MI value that is more than 3.84 and a correlation that is at least a medium effect size. But it doesn't make theoretical sense, so I'm not going to do it. Now, if you wanted to make a measurement diagram, we could use the function SEM_pass, and P is capitalized, and then that fit refers to the model that you just ran. What labels basically tells R that we want the fully standardized parameter estimates. Layout equals 3 is just basically one of the ways in which the one of the styles in which the figure is made. These are just basically different types of specifications for example, size of the font, that's edge.label.cex, and the margins. This goes from bottom, left, up, and right. And so I sometimes tweak around with this to find the best type of configuration to see my numbers. And so yeah, so this kind of gives me a visual of what's going on here with my factor model with men. Again, these values here represent the fully standardized parameter estimate. So these represent the factor loadings. These represent the error variances as well as the error covariances. These numbers here that are between the triangle and the boxes, these represent the item intercepts, more specifically, the standardized item intercepts. 1.0 is basically the variance of the factor, and 0.00 is the fully standardized intercept for the factor. So this just gives me more assurance that I'm running this according to how I think it should be run. All right, I'm going to do the same for women. So we're going to call this woman.fit. Overall model is still the same, basically this model right here. And we're going to apply this to the woman data set, excluding columns 1 through 3. And we want to estimate the intercepts. So mean structure equals true. It gives me those estimated intercepts. So when you look at the parameter estimates here, again, look for Haywood cases first. So look at my error variances. I don't see any negative values, so we're good. R squared should not be more than 1. And my standardized factor loadings should not be more than 1 as well. Okay. Those basically are just big red flags that your model is having a really tough time reproducing the variance covariance matrix. If you do encounter some Haywood cases, you need to check for data entry errors. You need to make sure that you got enough sample size. You need to make sure that you have enough of a reason to impose a confirmatory factor structure. If not, you might need to go back into an exploratory approach before you come back again into a CFA. All right, again, parameter estimates as a function gives me the confidence intervals. If I want a modification indices, I request it using the modification indices function. And as you can see over here, none of these correlated errors are a medium effect size. I mean, we could look at RS 10 and 11, I guess, if we wanted to. I can usually find something to laugh about. Unbelief in myself gets beat for hard times. Again, I don't see any conceptual reason to believe as to why these two things should be correlated. So let's check to see how we're doing in terms of the global fit indices for the women. So scrolling up here, chi-square is still significant, just like how it was with men. In terms of CFI and TLI, we're doing pretty good. 0.90 and above, these two values are. REMC, it's a little bit worse compared to men. It looks like this is 0.092, but still below 0.10, although the 90% confidence interval is above 0.1, which is not so great. And the standardized root mean square residual, that's pretty good too. So the point estimate of REMC is below 0.1, although this is probably not very great, so I should probably highlight that. But overall, taking into consideration these global fit indices, taking into consideration the fact that none of the model specifications, re-specifications based on modification indices were creating or were generating estimated standardized parameter estimates that were more than 0.3. I'm not going to modify this factor structure for women. I'm going to assume that they're about the same. Now zcorrel, I might have forgotten to mention what this is for. Basically, by using the residuals function and asking for standardized residuals, this gives us the standardized residuals, which is basically the estimated difference between your model implied variance covariance matrix and your sample variance covariance matrix. So if you wanted to, you could examine this. I will copy this into an Excel sheet and sort this to see where the focal areas of strain might be. This may or may not give you a very clear idea on what parameter estimates might need to be changed, but it'll give you a sense. If your modification indices tell you to change something, go ahead and check your standardized residuals to make sure that the pattern over here makes sense given the model re-specifications based on your modification indices. Now, if you wanted to make a measurement model, you're going to use SEMPAS again with P capitalized. We're requesting for fully standardized parameter estimates and using the tree layout, using these specifications in terms of formatting. H.label is 1.2. That's the size of the font. And then the margins are 2222. So this gives me this measurement diagram right here. And it's the same interpretation as how you would interpret it for the men's measurement diagram. All right. So I transferred the fit indices for women onto this Excel sheet earlier. And so given that we're doing about equally okay in terms of our global fit indices, let's take the first step and combine our men and women data set into a single variance covariance matrix. And start with the least restrictive type of model, where basically all we're saying in the configural stage of your measurement variance analysis, that we're basically saying that the pattern of items and factor is the same across men and women. That's all we're saying. We're not constraining any of the factor loadings. We're not constraining any of the intercepts. We're not constraining any of that to be equivalent to each other across male and female. We're just saying that the number or the pattern of item factor loadings is the same across men and women. So this is also known as configural fit. In case this doesn't make too much sense to you, in psychometrics, I think I showed you guys this diagram right here. When you do a multiple group confirmatory factor analysis, you start out with configural invariance, and then you move on to metric invariance, which is constraining factor loadings to be equal to each other across groups. Strong factorial invariance, basically meaning we constrain the intercepts to be equal across groups. And strict factorial invariance refers to constraining the error terms to be similar or equivalent across groups. We're not going to do this. Brown very clearly says that this is typically not required for you to make the conclusion that a measure is fully invariant. But conceptually, it is a thing that you could do as well. Okay, so how do you do this? Well, let's use the CFA function, apply that model that we've been using as we applied them to the male and female data sets. And we are going to group them based on sex, use the NOAA data set, and we're going to call this configural.fit. You'll notice in the next few steps, we'll keep adding more specifications in this line right here. All right, so let's get the parameter estimates and the global fit indices using the summary function. Again, this is pulling the parameter estimates for the configurable fit model. We want fully standardized values. We want the R square, and we want the global fit indices. Again, look for Hayward cases here. I don't see any Hayward cases in the R square. Neither do I see Hayward cases in the variances, and neither do I see Hayward cases in the standardized factor loadings. Let's look at the, and notice how it is creating two different sets of parameter estimates. What we just reviewed was for the women group. There are also parameter estimates for the men group. So again, looking for Hayward cases in the R square, in the error variances, and in the standardized factor loadings. And they all look good to me. In terms of chi-square, we are still significant, which is not surprising. But a CFI and TLI, they're still in a good range, right here. REMC is 0.084, which is not great, but adequate. And SRMR is 0.038, which is good. So I transferred those values over here. Basically, once we combine both men and women into the same data set and only constrain the pattern of item factor loadings, we get approximately the same degree of goodness of fit index. This code right here gives you the confidence intervals. I'm not going to run that because we don't need that for this particular video tutorial. Modification indices gives you the modification indices. If you want to look at the residuals, this is the code that you would use to do that. Now, one thing I do want to show you is this. When you make the diagram, notice that there is an instruction over here that says hit return to see the next plot. Basically, in the first plot, it's going to show you the parameter estimates for the first group, which I believe was women. And the next group, you hit enter again, it's going to give me the other measurement diagram for the other group. All right, so global fit indices suggest that our combined model is doing equally well. Let's check out metric invariance. Now, for sample sizes with adequate power, with equal group sizes, which ours is about there, and potentially some mixed invariance, which we're not sure, Chen suggested a criterion of negative 0.01, change in CFI, paired with changes in REMC of 0.015, and SRMR of 0.30 for metric invariance, or 0.15 for scalar or residual invariance. We're not going to look at a residual, we'll just look at scalar. But here, just to point out that the suggested criterion to determine if your model is significantly degraded in terms of fit does differ a little bit between metric and scalar. And Brown 2015 in his book, it looks at chi-square differences in its demonstration as it goes through the multi-group CFA. So we're going to take that into consideration as well. So we're being pretty conservative here in terms of our multiple group CFA. So the next step is to do the metric invariance. Now notice here, like before, we didn't have this verbiage that said group dot equals to columns loadings. Previously, we only had this, and we closed the parentheses. Now I'm going to call this metric dot fit. We're going to run the CFA based on the original factor model on the no out data set. We're going to group them based on sex, and we're going to constrain the loadings to be similar, to be equal to each other across the groups. So if, for example, the loading of RS2 on resilience is 1.117 for women, right? We're going to constrain that to be same for men, as in it needs to be the exact same value. Now the value is going to be different because it's going to look for the best parameter estimates taken into consideration both men and women, but basically we're constraining the factor loadings to be equal to each other. Okay, let's get the parameter estimates using the summary function. Oops, I must have screwed something up. Let's try that again. All right, so let's see. Let's look for Hayward cases. No R square is more than 1. No negative error variances less than, that are negative. No standardized factor loadings that are more than 1. And notice here that we have this interesting notation here that says .p2, .p3, .p4. Now these are the factor loadings that are constrained to equality. So it is 1.194 for the factor loading for RS2 on resilience for the woman group. It's going to be the exact same thing for the men group, which is 1.194. So that's one way for you to check that, to make sure that you are constraining the parameter estimates correctly when you look at the results. If you look at CFI, it's 0.946, PLI is 0.938, so that's pretty good. REMC is 0.081, which is acceptable. And SRMR is 0.052, which is still excellent. So I transferred these global fit indices to this row right here. And what we're doing, notice now that I have a couple of columns. This column here gives me the difference in chi-square value between the metric model and the configural model. And this right here tells me the difference in the degrees of freedom. Based on 13 degrees of freedom, we have a 15.05 chi-square value. I want to know if that is statistically significant. And to do that, I'll just look at a chi-square table. So again, the degrees of freedom here is 13. So 13 degrees of freedom and 0.05. The value for 0.05 is 22.362 in terms of the chi-square. So basically, any chi-square value larger than 22.362 is considered statistically significant because the p-value is going to be less than 0.05. And our chi-square value is 15.055. And the chi-square value over here is 22.362. So this is not statistically significant. So we're actually good in terms of constraining the factor loadings. So significance of chi-square is no. I'm also looking at the difference in the CFI values. Oops. And it's basically identical to each other. So it's 0. So CFI change is not salient. REMC, taking 0.081 minus 0.084. In this case, our REMC actually improved. Not surprising because REMC takes into account model complexity. It penalizes models that are too complex. So REMC is good. Standardized root mean square residual, you can see over here that it's gotten a little bit worse because this does not take into account model complexity. And we want this to be, and basically it tends to get worse over time because as we constrain our parameter estimates to be equal, that gives us our computer less options to work with in terms of being able to reproduce the variance covariance matrix. So the difference in SRMR is 0.014, which is still less compared to what Chen in 2007 recommended. It needs to be 0.030 to be considered salient. So we're good in terms of metric invariance. When we constrain the factor loadings to equality, our global fit indices do not degrade significantly, meaningfully or statistically significantly. Okay. Now, moving on to scalar invariance. Now, this is when we equalize the factor loadings and intercepts. And actually, before I go into that, I do want to show you a quick diagram here. When we say equal factor loadings in the metric invariance, we're basically saying we're looking at this essentially. We're saying that as the estimated change in your latent factor goes up by 1 unit, the amount of change that goes up in your indicator, say x2, goes up by the same amount of units. That doesn't mean that your intercepts are the same. When you're talking about same intercepts, you're talking about scalar invariance. So far, we've only got this down, which is better compared to something like this. You know, if if we did not have metric invariance, that means that our items have different degrees of their relationship with the latent factor. So we can tell over here, for instance, that as the latent mean changes by 1 unit, group 2 changes, but not as much as group 1. And so this is not metric invariance. This is also not metric invariance. This is metric invariance. Okay. Now, let's constrain our intercepts to be equal to see if we actually have something like this in terms of our relationship with the indicators and the latent factor. So this is called scalar.fit. Actually, you can call this anything you want, but just for the sake of keeping track of the steps here, let's just call this something intuitive. It's scalar.fit. So function here is CFA. Notice now that we are not just constraining the loadings to equality, we're also constraining the intercepts to equality. Let's get the parameter estimates here. Notice here that the intercepts are not constrained to equality. Same thing with the factor loadings. That's referring to the woman group, and we should see the same thing for men. Intercepts and factor loadings constrained to equality. I'm not going to check for Haywood cases because I've checked for this already. And basically, you're unlikely to encounter Haywood cases as you go through your steps of a multi-group CFA. That would only be a lot more important for doing a CFA for the very first time. Here's the code for getting modification indices if you wanted to. But we don't need to look into that yet, I think. But let's see what's going on here. So CFI is 0.941, Tucker-Lewis is 0.937, RMC is 0.081, SRMR is 0.055. So overall, fit indices are doing okay, but did they degrade significantly? Well, I took basically the difference in chi-square between the scalar model and the metric model, took into consideration the difference in degrees of freedom. And according to this, with 13 degrees of freedom and having a chi-square value of 36.2, that is actually significant. Because with 13 degrees of freedom, any value that is more than 22.362 is statistically significant. So yes, it is significant in terms of chi-square. CFI doesn't change that much. So that's not salient, that's not more than 0.010. RMC doesn't change. And SRMR doesn't change that much as well. Oops, actually, I'm looking at the wrong cell. I'm looking at this one. Right there. Now, at this point, some researchers may still go ahead and say that, hey, we've actually achieved full measurement invariance, because really, chi-square as a test tends to be, again, it tends to be trigger friendly when it comes to being able to, when it comes to saying that there is a statistically significant effect. Now, for the purposes of this tutorial, you can be extra conservative, and let's just say that we're going to conclude that even though CFI, RMC, and SRMR don't have significant degradations of fit, the chi-square does say that we have quite a bit of degradation. Let's go ahead and release the intercepts one by one and see which is the intercept that, if we were to allow it to be free to vary across groups, that would give us the most bang for a buck. That is basically going to give us the most amount of improvement in terms of our model fit. And so to do that, we need to use this line of code right here. Now, first of all, we need to create a models. So models, and followed by this arrow sign. We're going to list the models here. Fit.configural, and I have a note over here that the names that come first, like fit.configural, are the specific terms that you need to specify, while the names that come later are the names that you had previously assigned to your models. So previously, for the configural.fit, I named it configure.fit. And so this can be anything that you had named it prior to. This one here needs to be the same across whatever analysis that you do. So fit.configure is basically my model that I just ran, the configure.fit. Fit.loadings is referring to the model that I had constrained the factor loadings to be equal. And fit.intercepts is referring to scalar.fit, which is the name of the model that I just ran. And the reference group will make the number 2 be the reference group. This could be number 1 as well. It's either way. So we'll run that. Now we're going to use the partial invariance function in order to figure out which item we would want to release in terms of its constraint to equality across the groups. It basically frees the, not residual here, the intercept constraint sequentially for all items, and it gives me a chi-star change, the CFI change, as well as the wall test results. Thinking. All right. Usually there's some kind of warning over here. That's usually not a big deal. I'm going to pull up the parameter estimates here. And what I would do is I would copy and paste this entire thing. And let's see if we can paste this. Let's start a new. Okay, I'll fix this later, but let's paste this here first. We'll do text to columns. And I want you to look at this value right here. Now, basically, I'm going to sort this first. This is sorting it according to the largest change in your CFI values if you were to allow the RS1 intercept to be free. And so you would want to basically sequentially release the intercept constraints, starting with the one that gives you the largest change in CFI value if you were to fix it. The negative here basically tells you how much your CFI global index reduces if you were to fix it right here. Your wall test basically tells you how statistically significant your difference in global fit might be if you were to constrain this to equality as well. And this here gives us a statistically significant wall test. So RS1, if we were to fix it to equality across groups, that's going to give us the largest degradation in our CFI fit. So what we're going to do is we are going to, first of all, release the intercept of RS1 to be free to vary across men and women. So that's basically what I mean over here by copy and paste the results into Excel and sort. All right, so the syntax over here, let's call this partial.scalar.fit.1. And again, you can call this whatever you want, but it's useful to name this systematically. CFA is the name of the function. Overall model is the name of a model. The data set, the groupings, and notice that now we are constraining the loadings and intercepts to equality. And in addition to that, we are partially allowing the intercept of RS1 to be free to vary across groups. So that's what group.partial means. Let's get the fit indices right here. Notice here, for instance, that RS1 is now no longer constrained to be the same across groups for women as well as for men. And I copied and pasted the global fit indices onto this Excel sheet, which is right here. Partial scalar for RS1. So overall, global fit indices do well, but did it significantly degrade in terms of fit compared to the metric model? Now, it's important that you compare this to the metric model because this is what we were comparing our scalar model to. And you always compare this back to the metric model to determine if your partially invariant model might be that much different compared to your metric model. And unfortunately, we can see here that your chi-square is still different. Just to show you the formula, I'm taking this minus this in terms of chi-square. Same thing with degrees of freedom. And with 12 degrees of freedom, 30.89 in terms of chi-square, that is statistically significant. And that is coming from this table right here. In terms of our CFI, they are still pretty good, actually. Now, I'm going to save you guys some time here in this video tutorial. Basically, I did this one by one. After releasing the parameter estimate for RS1's intercept to be free to vary, I came to the conclusion, basically based on these results, specifically this one right here, that our chi-square difference is still different. Didn't quite bring us up to the right amount in terms of a non-significant chi-square change. So we're going to do the same partial steps earlier for the partial strict solution. I'm going to call these models 2. And now we are going to replace the fit intercepts model with the partial scalar model that we just created. And we are going to run the partial invariance analysis here. So it'll do the same thing again. It's going to free up the multi-group intercept constraint sequentially and tell us which is the item intercept, which is the next item intercept that is going to give us the best improvement in model fit. I believe that's referring to the one here at the very top. I'll make sure I'll fix this Excel sheet so it's not so ass backwards. As you can see here, RS1 doesn't really give us a whole lot of information here because we've already allowed RS1 to be different across the groups. RS12 is the next one. I believe I've already sorted this. Yeah, I've already sorted this in terms of the largest value. So basically what this means is that if we were to fix RS12 in terms of its intercept to equality across groups, that is going to change or degrade our CFI fit by this much value. So it's the second biggest one. That is going to be the next one that we will allow to vary. So we're going to rerun the partially strict model now, not just with RS1, but with RS12. And let's pull the parameter estimate. So notice here again, now it's RS1 and RS12 that have intercepts that are free to vary. I transferred the global fit indices from this output over here to this Excel sheet, which is this right here. And unfortunately, our chi-square difference between this model right here with RS1 and RS12 being allowed to freely vary compared to the metric model, it is still statistically significantly different. I'm going to save you the time of me going through every single step here. I'm just going to go ahead and run the code. Basically, I had to allow the intercepts of RS1, 12, 7, 6, 5, and 4 to be free to vary before I was able to say that the chi-square difference was not significantly different. Okay, so this is for the third step. Let's rerun models right there. Model number 4. run. This time for model number 4, we are allowing intercepts 1, 12, 7, 6. And that still wasn't enough. I think at this point we are right here. Still need a couple more. 5. Now we're allowing RS5 to freely vary. So not good enough, according to this right here. So one more item. All right. And that was when we finally were able to find a non-significant difference between our partially invariant model with the metric model. So interpretation is this: the resilience scale was partially invariant across intercepts, with items 1, 4, 5, 6, 7, and 12 being non-invariant across genders. Let's go ahead and compare the latent means across the groups, taking into account these non-invariant intercepts. So I'm going to pull the parameters from the partial.scalar.fit.6 because this was the last, basically the final model that we had arrived at. It basically gives you all the parameter estimates from the model right here, ranging from factor loadings as designated by equals tilde to the error terms to the intercepts. Now, we're going to make a set of factor loadings for men using the subset function. We are pulling information from this parameter object for only group number 1, because that's for men. Operation equals tilde, because that refers to factor loading. And we want the estimated parameter estimate. So that refers to this column right here. So how you read this is basically we are creating or subsetting some values from the parameters object for males. Specifically, we want the factor loadings in terms of the unstandardized parameter estimates. And if you were to run this object, you'll see basically that these refer to the unstandardized factor loadings from items 1 through 4. Do the same thing for women. So group number 2 instead of group number 1. These are the unstandardized factor loadings for women. Notice here that they're exactly the same, because as we had talked about before, we were able to achieve full invariance in terms of metric invariance, just not in terms of intercepts. So now let's extract the intercepts. Using a very similar line of code here, we're going to subset from the parameters object, specifically for group 1. We want the item intercepts in terms of the unstandardized parameter estimates. We call this men intercept. Now the problem is this: if you were to count the number of parameter estimates here, we actually have 15. Why is that? Because this last value right here is actually the intercept for the factor, not the intercept for the indicator. If we were to run the model again, you'll see here under intercepts that we have the intercepts for the indicators, and the last one is actually the intercept for the factor. We don't need the intercept for the factor for what we are about to do, because we only need the item intercepts for us to use later on in a formula to calculate our latent means. So basically, we are going to remove the 15th row from this array of numbers here. So the 15th row is this one. That's why we got negative column 15. That should give us basically these values, all 14 values except for the last one. We're going to do the same thing for women. Pull the item intercepts for women in terms of their unstandardized parameter estimates. We still need to remove the last one because that's the intercept for the factor. So minus the 15 row, that gives us this. So now we have a vector of factor loadings for men and women, and we got another vector of item intercepts for men and women. So to figure out the latent means, we need to subtract the item intercept from each person's observed score and divide the result by the unstandardized factor loadings. This basically comes from this slide right here when we talked about in class, when we discussed this formula right here. Okay. So the mean of a given indicator can be reproduced by the model parameter estimates based on the indicator's intercept, the factor loading, and the latent variable mean. Now, in this case, we're actually going to want to estimate the latent variable mean. So we'll need to take the respective indicator intercepts, and we are going to subtract the we're going to take the mean of a given indicator the mean of a given indicator minus the intercept of the that indicator and divide that by the factor loading. And that should give us the estimated latent variable mean. So subtract the item intercept from each person's observed score and divide that result by the unstandardized factor loading. Now this note over here on if you have multiple factors, you want to basically calculate multiple factor intercepts. In this case, we only have one. So first of all, we're going to create the operation for this, where X represents the person's observed score minus the item intercept for women. Divide that by the factor loadings for women. I'm going to call this the woman operation. And we're going to apply this woman operation across rows. 1 means rows and 2 means columns. And we're going to apply this for columns 4 through 17, because remember, the first 3 columns were the demographic variables on the women data set. So let me read that one more time. We're going to apply the woman operation across rows on these columns right here, because the first 3 columns are the demographic variables. And that gives us the estimated factor intercept for each person, all 516 people. We're going to do the same thing for the men intercept. And that. Basically, that gives us the estimated factor intercept for each person. Now, next we need to save the data as a data frame so that we can later on do a t-test. So just use the function as.dataframe for men factor intercept. And we're going to use this view function to let you see it. You'll notice here that basically what has happened is now the rows represent the items and the columns represent the people. So we need to flip that using the t function. We're going to flip it so it's people per row. So when you view it again, now it makes a little bit more sense. We've got 14 items and the rows represent all the people. Do the same thing for women, basically. All right. So now we've got the estimated factor intercepts for men and women. Then we are going to pull the average for the woman factor intercept for each person, and the average for the men factor intercept for each person, using row means as a function. See over here that each person has an estimate average of their latent factor mean. Same thing for men. We've got the estimated factor intercept for each person. So now we can do a t-test. Using t.tests, we're going to compare the men latent and the woman latent vectors. This is going to be a two-sided t-test. This is not paired, meaning this is not a longitudinal type of data set. We're going to assume that the variance equals true, and NA.action equals true basically means that work with the ones that have data. As can be seen here, the p-value is 0.6022. The estimated mean of X and Y. So this is the estimated factor mean for men versus women. And you can see here that there's not too much of a difference in terms of the values. That's why the p-value is not statistically significant. If you want a standard deviation, use SD as a function. And that gives you the standard deviation for these means right here. If you want the effect size, use cohn.d as the function. That gives you the 95% confidence interval for the man latent and the woman latent estimates. All right, so that's pretty much it in terms of the multi-group confirmatory factor analysis. By the way, when I say the effect size, this is basically the difference between these two means. And the difference is negligible, basically. All right, so that's pretty much it. That's all I have in regards to how would you do a multi-group confirmatory factor analysis. I hope you found this tutorial somewhat helpful to give you an idea on how to do an MGCFA. If you need some of the resources that I mentioned here in this video, feel free to reach out to me. If you have questions, feel free to reach out to me too. That's all for today, and take care and stay safe.